So in the last talk, I talked quite a lot about multiplication gates, addition gates, custom constraints, selected polynomials, copy constraints. Now we're going to discuss lookup constraints in a lot of detail. I'm going to spend a full hour on this. So remember the example I gave in an hour ago? I said, here's this very simple constraint system. We're going to prove that something is within a range between 0 and 4. We're going to do it with multiplication gates. We're going to do it with addition gates. We're going to do it with copy constraints. And at some point, I gave you a way of doing this which looked like this, which, as you can see, is quite a lot of constraints, so many constraints that I even managed to forget a couple of constraints, and there's some very, very small copy constraints that I put in there which I realized halfway through that I needed. So there's quite a lot going on there. If you are to, instead of going through this entire process to do a lookup argument, to do a range argument, use a lookup argument, I'm going to claim that you can do it in one constraint. So this is sort of both very helpful in terms of actually simplifying the problem of how are we going to arithmetize things. It's going to make things a lot easier to arithmetize because you're just going to have less going on. And it's also going to make things faster because your total number of constraints is going to be much less. I have been told that apparently figuring out the best way to use lookup arguments for things like SHA-2 and SHA-3 is not the easiest problem in the world, but it still does make a big difference. So what we're going to do in a lookup argument is we're just going to try and prove that some witness value x is contained in some table T. Of course, we're working with polynomials, so when I say a table T, I mean a polynomial that evaluates to the points in the table at certain points, 1, 2, 3, 4. So what we would be trying to do in this particular example is we would be trying to say that x is either equal to t1, or x is equal to t2, or x is equal to t3, or x is equal to t4. It's allowed to take on any of those values. Of course, we're not just working with one value x, we're working with an entire witness, and we would be trying to say that we have our witness polynomial a of x, which is going to evaluate to our actual witness points, a1, a2, a3, a4, at 1, 2, 3, 4. And we then want it to be the case that a1 is range constrained, and a2 is range constrained, and a3 is range constrained, and a4 is range constrained. So all of those values should exist somewhere in this table. In the last talk, I sort of focused on the fact that sometimes you have selector polynomials and you want to turn them on and you want to turn them off. So it could be the case that maybe you want to have that A1 and A3 are range constrained, but everything else is not range constrained. But for the interest of keeping things simple in this talk, I'm going to completely ignore that. I'm also going to claim that there are some situations where you would ignore that. Like, for example, if you're working over an architecture which is handling uint 32s, it might very well be the case that you want your constraint system to just automatically enforce that everything is a uint 32 and not worry about that. And if it's cheap to do, which these lookup arguments are fairly cheap, then this is something which you would seriously consider. So the first lookup argument I'm going to be talking about is the Halo 2 lookup argument. This is not the lookup argument that everyone was using before. In particular, the pluckup argument is probably the one that came first and is a little bit faster. But the Halo 2 argument is very nice to explain. So that's the one that I'm going to explain. If you want to find the actual reference, it's not a paper, it's not on ePrint, but there is a book. It's like an online book, so I'm not sure what the correct word for that is. There is a book which can be accessed for free at the link that's on the slides. So a reminder, what we're trying to do is we're trying to prove that AI is included in this table T1, T2, T3, T4 at all points I in 1, 2, 3. 0, 1, 2, 3. I've started indexing from 0 there, that was a mistake. I'm first going to try and fail at a couple of things. I'm first going to try and use a copy argument. It's not going to work. I'm then going to try and use a permutation argument. It's also not going to work. And then I'm going to actually explain what it actually does. Okay, so we have our set of witness values, and we have our table. And we want to try and prove that every single witness value is included in this table, and we want to do it just using copy constraints. Well, let's say I have the copy constraint A1 equals T1. In the particular case where A1 does in fact equal T1, then we're good, I can prove the stuff. At any other point, I'm not going to be able to prove it, because what if A1 is actually equal to T3? That would be a valid entry in the table, that would be a valid entry for A to take on. However, it's not covered by our copy constraint. A1 is not going to be equal to T1 in this case, so a prover wouldn't be able to convince a verifier of a true statement. So that's not going to work. If we instead have a permutation argument, this does give us more flexibility. In particular, we can say that A1 is either equal to T1 or T3. But we're going to have a situation if any points in the table are repeated in our witness. And so in this example here, we have that both A1 and A3 take on the same value T1. So when we do our permutation, we actually have that T1, T2, T1, T4 is not a permutation of T1, T2, T3, T4. So again, we're not going to be able to prove a valid statement. I'm going to claim that what the Halo 2 argument does instead is it sort of has this four-step process. You first do a permutation argument to get to a temporary table C. You then do a copy this or that argument, which I will explain in much more detail, to get to another table D. And finally, you permute again in order to get your final witness, A of X. And I'm just going to walk through an example of a situation where we might be using this argument and why it will work. Okay, so let's suppose that we have the witness T2, T3, T2, T4. All of these are valid entries in our table, T1, T2, T3, T4, and we want to prove that this is in fact the case. The first thing we're going to do is we're going to take all of our witness elements and we're going to try and order them. So in this particular situation, how would we order 2, 3, 2, 4? Well, we'll take that as 2, 2, 3, 4, and that will be our ordering. We're just incrementing by when the first entry appears in our witness, we're going to take that, and then we're going to look for all of the repeats of that value and put them all together in the same place, and then we're going to increment in that fashion. We're then going to go to our copy this or that argument. So every entry in D of X, we want to either be a copy of the exact entry in C of X, or we want it to be a copy of the previous entry in D of X. So in the very first situation, D1 clearly isn't a copy of anything. It's the first time it appears. So we have that it must be a copy of the first entry of C1. So C1 is going to be equal to T2 in this particular case. However, for our second constraint, we have that D2 is in fact a copy of D1 because T2 is equal to T2. Therefore, we can say D2 is a copy of D1, and we don't need to put anything in our temporary table C. We can leave that spot blank. In our third slot, T3 is not a copy, so we need to copy it over to C. And likewise, in our fourth slot, T4 is not a copy, so we need to copy it over to C4. So we now have a temporary table C, which has one empty slot. We know that the first slot must contain T2, we know the third slot must contain T3, the fourth slot must contain T4, but that second slot is unconstrained by our temporary table D. So then when we want to run our final permutation argument to the table of allowed values, we can choose the empty slots to contain the values that we need them to contain, which in this case is going to be equal to T1. So then that would, following these three steps, take us from our witness to our table. This would be a good point for questions if anyone's confused, by the way. Cool, I'll move on then. I'm not going to discuss how the permutation argument works because that's been discussed in prior talks today. But I am going to discuss how the copy this or that. Yeah?
So I just was going to ask you to remind me, what's the complexity of the permutation argument?
The permutation argument is going to be n log n in the size of the table.
And that's not the first prime permutation, that's any permutation.
Yes, this would be any permutation, a permutation of choice. But the complexity is actually very similar for a permutation of choice compared to a known permutation. It doesn't really affect your costs much at all. So when I say copy this or that, this is a term that I came up with like a couple of days ago, so don't expect to be able to Google that, but I think it accurately portrays what's going on. Yeah?
If we didn't have P1 before, like really running the final table, I don't think we understand why we need the P1.
Well, we need that the table C is a permutation of table T if we want to be able to run a permutation argument.
What would fail in the permutation argument if we would have two T2s?
If we had two T2s, well, if I go back quite a lot, yeah. In this situation, it's not T2, it's T1. If we had T1 appear twice, can you see that T1, T2, T1, T4 is not a permutation of 1, 2, 3, 4?
Right. Oh, so we have to have 4 different elements in permutation argument to raise the level.
Yes. Okay, so in our copy this or that argument, our aim is to show that at all points I, either C of I is equal to D of I, or D of I plus 1 is equal to D of I. One of those two constraints must hold. And the way we're going to do this is just, honestly, brute force. It's not going to be pretty. So the first step, if we want to show that Ci is equal to Di, well, this is an equality constraint, so we're just going to check whether C of x minus D of x evaluates to 0 over the domain. And in this particular case, we do have that Ci is equal to D of I, so that constraint will be satisfied. I recall here that Z of x is a vanishing polynomial, so it vanishes over the domain. However, in this particular situation, this equation is not going to be satisfied in the situation where D of I plus 1 is equal to D of I, which is a value which it is allowed to take on. So we're going to have some situations where the prover isn't able to convince the verifier. So we're going to need to be just a little bit smarter than this. What we're going to do is we're going to introduce a binary polynomial. This binary polynomial is chosen by the prover. And they're going to choose it so that at every slot it's either equal to 0 or it's equal to 1. And we have to actually check that this polynomial is a binary polynomial because it's chosen by the prover, and therefore it could be the case that the prover chooses something that's not a binary polynomial and lots of bad stuff happens. So to just enforce that it's a binary polynomial, we're going to do the standard trick. We're going to check that b times 1 minus b is equal to 0, but we have to do this over the whole polynomial, so we take the identity polynomial, a polynomial that is equal to 1 at all of the points that we care about, and we're going to say that b of x times the identity polynomial minus b of x is equal to 0 over the domain. Okay, and this is going to enforce that at all points I, b of I is either going to be equal to 0 or it's going to be equal to 1. So then in our situation where Ci is equal to D of I, we're happy. It evaluates to 0, B of I can equal 1, and the constraint is satisfied. And in the situation where Ci is not equal to Di, the B of x is going to be equal to 0. So nothing's going to happen there. But we do need to add a little bit more, because in the situation where D of I is equal to D of I plus 1, we need that to be the case that that constraint is actually constrained, and we're not just letting the prover cancel out all of the interesting stuff that's happening in the polynomial by multiplying it by 0 and then leaving it as is. That would be a very insecure system. Instead, we say, okay, in the situation where b equals 1, we're going to check that d of x minus d of x minus 1. So we're going to have to do a shift inside the constraint here, the d of x minus 1. In practice, this would be roots of unity, so you'd multiply it by omega, but because I'm working in this sort of convenient basis, x minus 1, and we're just going to check that either one of these is going to be equal to 0, and therefore the constraint must be either this or that.
You choose the same treatment as for the binary integration. So like the z then just like z minus 0 times z minus 1.
Because the constraints that we're doing here, the this or that, with our binary constraints, they're applying over our whole witness at the same time. So we're going to be adding on one constraint there per witness value, whereas if you want to do the binary decomposition for every single witness value individually, then you're going to have a logarithmic number of constraints. So the total number of constraints you're going to have to do in this situation is going to be less. Okay, so I claim that this works. I'm not actually sure whether this is what the Halo 2 people do, by the way. It's what I'm guessing that they do when I was trying to figure it out on paper myself. But it would be the natural thing, so I would guess it probably is what they're doing. Okay, so going back again, we have a permutation argument, and then we have a copy of this or that argument, and then we have a permutation argument. And this is sort of a very nice lookup argument in the sense that it's going to work in a transparent setting. It's going to work over normal discrete log groups. It would also work in a Frey setting if you are using the Frey polynomial commitment scheme. However, if we happen to be using pairings, we can do better. In particular, if we want to have a very large range table, in the last talk, we were saying that your SRS is usually bounded by 2 to the 27. That's the biggest setup anyone's ever done. So let's say you want to have a range table that goes from anything up to 2 to the 27. If we want to do this particular argument for such a large table, it's going to cost us some overhead. In particular, we have to run a permutation argument over the entire size of the table. So in the situation where the table is actually much larger than the witness itself, which if we're talking 2 to the 27, it very well could be, then that's going to be a cost that your prover would have to pay, which we would rather not pay. You probably would choose to just work with a smaller range if that was the case. You really don't want to go over the size of your witness in this particular lookup argument. My claim is that over the past year, there's been lots of work coming out on lookup arguments and trying to do them more efficiently. In particular, we want lookup arguments which are independent of the size of the table. I'm going to take some partial credit for sort of setting this off, but the Calc Plus result was a very sort of good one in taking a table and then switching to a smaller table filled with the values that you're actually using in your actual lookup argument in a way which is completely independent from the cost of the actual table itself. This sounds impossible. It's not impossible, and the reason it's not impossible is because we have pre-processing. Without pre-processing, though, it is impossible. So if you have a temporary table that you're trying to use in your ZK EVM, this would not be the trick for you. And the reason it works so nicely is because KCG proofs have this really nice algebraic structure. All you're doing in a KCG proof is you're just computing the polynomial evaluated at a random point x in the exponent, and everything's homomorphic. You can add things, you can multiply things. You can't multiply two unknown things, but you can multiply a known thing by an unknown thing by a known thing. And when you have your proof that your polynomial commitment has been opened at a particular point, this proof is a non-interactive proof. And when I say non-interactive, I don't mean it's been made non-interactive using Fiat-Shamir. I mean non-interactive, strictly algebraic, combining the elements in the group that you already have. Which means that there are a bunch of tricks we can do. One of which is if we want to compute not one KCG proof, but 100 KCG proofs at some specific points, that is not going to cost us 100 times the cost of computing one KCG proof. It is in fact going to be n log n. So it's the overhead you're paying for computing many proofs is very similar to the overhead that you would be paying for computing one proof. And this is very important because otherwise the setup cost would be quadratic, which is generally considered to be fairly impractical. So we have a setup cost for generating all of the possible openings of our polynomial commitment, which is going to be n log n. The commitments that we're opening are in fact going to be opening proofs that our table T of x is going to evaluate to our entry T of I at the point I. That's all it's doing. Okay, so suppose we want to prove that we have a subtable of entries and we want to have that our subtable contains all of its entries from the original table T of x. We have these preprocessed polynomials. They're something that we're going to be able to use. And the question now is going to be, how are we going to do this? We're going to consider that our subtable, this C of x, is defined not over the entire field, but over a specific field I, which is a subset of our entire field. And actually, this is going to be an unknown subset, which is going to make things a bit harder. The prover knows what I is, but the verifier doesn't. So my claim is above. If C of x is defined over I, so C of x defined over I is a subtable, then T of x minus C of x is equal to something which vanishes over the vanishing polynomial defined over the set I. So this is going to look a lot like our original vanishing polynomial, but we're just not going to multiply it by the points that we don't care about. So at all points, I and capital I, we're going to require that Ci is equal to Ti. In the situation where I is not in I, though, we're not going to do anything. And if we want to check that our vanishing polynomial actually is a valid vanishing polynomial, this is quite easy. We just check that it divides the full vanishing polynomial. With me so far? So remember, I have these pre-computed values. Where C of 2 is equal to T of 2, we are in fact going to have that Q2 is a valid proof that C2 is an opening of T at 2. Likewise, Q3 is a valid proof that C3 is an opening at 3, and same for C4. And my claim to you is that if we have a commitment to Q2 and to Q3 and to Q4, then actually it's very, very fast to compute a function that will take these three commitments to the full polynomial Q of x that we need in order to prove that C is a subtable. I'm not going to tell you how to compute this function. That would take a long time. But I am going to sort of claim that it doesn't depend on the values that it's not using. So in particular, it's not going to depend on Q1 here because Q1 is not used. Computing this function takes n log squared n, where n is the value, the size of the subtable. So it's not quite linear, but it's not far off. What else is there that's interesting to say about this particular function? What we're using here is we're using that the commitment is really a group element. It is a single group element that we can apply linear transformations to. Yep?
Is there an underlying assumption here that like we have a set which is big, but in our proof we only need the subset of this set? Because what if we want to prove that, like what if we want our set to be all other elements, all like we want to prove?
So if you're using your entire table in your witness, so your witness is at least as big as the size of your table, you probably wouldn't use this strategy. You'd be better off using the Halo 2 strategy that I was describing before. This is specifically talking for the case where you have a very, very big table and a smaller witness. So there are going to be some entries in your table which are unused. Yep.
I think I'm missing where this can be applied, because you're saying that this is going to be done during pre-processing, right? But if it's done during pre-processing, then how are you going to, either everybody knows which subset of the table you're going to use, in which case you can just make that your table, or you don't know, and then the pre-processing won't apply, right?
So pre-processing is for computing Q1, Q2, Q3, Q4.
But those require knowledge of which subset you're going to need, no?
No? No, they don't. Those literally depend on, well, your universal setup for generating your polynomial commitments, and they also depend on your table T. So you do need to know what the table is in advance, but you don't...
You need to know the size of the subtable, actually.
You do need to know the size of the subtable, yes. Yep.
We start with the giving us this an algorithm in a case that we have a really long table, and now you said that the complexity of this function, like computing this function, is n log squared n. So
In the size of the subtable, not in the size of the full table. So we now have a subtable C of x, and we're going to be trying to run a lookup argument, not with respect to our full table, but with respect to our subtable. And this is actually not going to be the easiest thing in the world, in particular because our subtable is defined over an unknown set I. So what we're doing in blue is we're precisely trying to say, if we have a set I that we don't know, all we know is that it's a subset of our full set, how are we then going to run a lookup argument? So we want a way to get from our subtable C of x to our full witness A of x. The general idea sort of is building on work from Aurora back in 2019, and in particular they have a lin check argument. And in their lin check argument, they're able to check a matrix equation. So they're able to check that E of ij times C at j, where we sum over j, and notice that j is running over the set I here, and not the full set, is equal to ai. Okay? That's what they're proving in that particular paper. And in our case, this is sort of already going to help, because if we have this matrix, then we are going to have a way to map from the C entries, T2, T3, T4, to the witness entries, T2, T2, T4. That is some matrix equation. But actually, we're not going to allow any matrix in this situation. We're specifically going to require that our matrix contains unit vectors. So in this particular case, we have that the unit vectors can be equal to 1, 0, 0, or 0, 1, 0, or 0, 0, 1. They're not allowed to be anything else. If we wanted to have a matrix of unit vectors mapping this particular example, C of x to A of x, well, our first unit vector would be 1, 0, 0. That maps T2 to T2, as we need. Our second vector is also going to be 1, 0, 0, because we need to map the first entry of C of x to the second entry of A of x. And our third unit vector would be 0, 0, 1. And the thing I want you to note here is that we do have a repeated value in our matrix, and this is something which is completely allowed. As long as it's a unit, we're happy. Good so far? Of course, I'm talking about vectors here, and I'm talking about matrices, but I have previously told you that everything we're doing, everywhere, anywhere, is polynomials, and so we need to be talking about unit vectors, but we kind of need them to be polynomials. How are we going to do this? I claim that if you sort of look at it in a kind of hazy way, you can kind of see Lagrange polynomials as being like the unit vector in your evaluation domain. So if we just sort of recall what a Lagrange polynomial is, it's a polynomial which is either going to be equal to 1 if x is equal to I, or it's going to be 0 if x is not equal to I over all points I in your domain. If we actually look at this in terms of like polynomials, we have this product equation going on here, which is just going to define what this Lagrange polynomial is going to look like, and this product is going to hold no matter what your domain is. In any domain, this is what the Lagrange polynomial will be. I'm going to rewrite this slightly, and I'm going to say that we have the product that we're interested in, the product x minus j for all j not equal to I in the domain. Then the Lagrange polynomial is going to be equal to tau I of x divided by tau I evaluated at I. This is just a more convenient way of thinking about it for the sake of Baloo. In particular, the tau I of x polynomial is actually equal to a full vanishing polynomial zi of x, which is something that we're going to have a commitment to, divided by x minus I for some I in the domain. Which means that then when we want to compute our unit vector, we have that Li of x is equal to tau I of x divided by tau I of I, which is then something we'd be able to evaluate. So if we plug this back into the lookup argument that we're working with, we have that the unit vectors, rather than the Eij up there, we're using the polynomials, and we're saying that Ei of x is equal to tau I of x divided by tau j of v for some v. And the point is here is that we really don't care what v is, because the prover can't choose malicious v. If the prover chooses some v which is not in the set I, then the polynomial tau j of x is not going to be a polynomial, because it's not because it's not a polynomial, it's not something that the prover can commit to. So, as long as it's equal to zi of x divided by x minus v for some v, we know that this is going to be a valid unit vector and something which we can use in our equation. And once we have proven that we're working with unit vectors, we can then prove our lin check argument using the Aurora sum check technique.
So the prover sends
The prover sends a commitment to all of the v's, because there's going to be a different unit vector at each slot. So we're going to have a polynomial v of x, which is going to evaluate. In this case, it would be to 1, then 3. And then we would be able to prove that we have computed each of the tau j's correctly with respect to zi of x and the commitment v of x. The technique that I've been describing here, it's costing m log squared m. Recently, and when I say recently, I mean very recently, I mean a month ago, there has been a follow-up work called CQ, which manages to improve on this yet again. So it's taking things down from m log squared m to m log m, for m the size of the table. And really the way that they do this is via an alternative pre-computation technique. Rather than directly computing the opening proofs for the table T of x, they're instead computing the opening proofs for the polynomial T of x multiplied by the Lagrange polynomial at each point I. And from these pre-computed values, they're going to be able to prove an alternative equation. What they're going to be able to prove is like this quotient type equation, where they're going to say that there exists some m such that the sum over all tj of mj divided by y plus tj, where y is our indeterminate here, is equal to the sum over all ai of 1 divided by y plus ai. These m values are very much allowed to be 0, and this is important. Because if you have something which is essentially going to contain the entry 1 divided by y plus tj, and you're trying to sum over it, in the situation where m equals 0, you don't sum over it, and you completely ignore it. And likewise, when we're summing over all AIs, if AI is repeated, right? Sorry, if AI contains a repeated entry, let's say A1 is equal to T2 and A3 is equal to T2, then you would just set that M2 is equal to 2, and this sum would still hold. And the sort of real trick here is that they're not going from the table to the subtable to the final witness. They're doing it directly. They're taking their table, they're just saying, these are the entries we actually want. When we don't want them, we set them to 0, and we're going to sum those all up and check that the sum is equal to what we need it to equal. And I'm expecting to see sort of more works in this area, but this is currently the state of the art. Okay, so those are the 3 examples of lookup arguments that I'm going to run through. How am I doing for time, by the way? 10, 15 minutes, perfect. I'm going to sort of move on from that. If there's stuff that you weren't understanding in the sort of previous slides, then don't worry about it, because I'm not going to talk about them again. Instead, what I'm now going to talk about is a way that we would use these lookup arguments inside our Plonkish constraint system. I've already mentioned range checks as being a very, very big application of them, one that you would use all the time. But actually, there's more that we can do than just range checks. We can also do something that I call function tables. So remember before, we have the witness values and the table of allowed ranges, and we have these 2 columns. But when I was talking about Plonkish, I wasn't talking about there being 1 column per witness value. I was talking about there being potentially many, many columns. So let's go back to the situation where we have a witness containing lots of columns. In this situation, 3 columns. So we've got an A column, we've got a B column, and we've got a C column. If we have a table, it's also perfectly okay for our table to contain multiple columns. So in this case, I've got my table containing a T column, an S column, and a U column. And this would also be something that we're able to commit to. So if we have sort of these wider witnesses and these wider tables, then we can do some function lookups. So as an example, we would be able to do a lookup argument for proving that AI or BI is equal to CI. How would we do this? Well, first, we're going to put all possible inputs and all possible outputs to AI or BI is equal to CI into our function table. So either we have 0 or 0, that will map to 0. 0 or 1 maps to 1. 1 or 0 maps to 1. 1 or 1 maps to 1. That would be our function table. And what we now want to prove is we want to prove that each entry, AI, BI, CI, for all I, is included in TJ, UJ, VJ for some j. If this is the case, then it must be the case that AI or BI is equal to CI, because it's in the possible range of inputs and outputs. Questions? The lookup argument I gave you was working for single inputs and single outputs. All of the lookup arguments I was giving you, this was the case. And we have these columns, well, what are we going to do? We're cryptographers, we don't have many tricks, we really have very few tricks. But one of the tricks we do have is random linear combinations. So we're going to view AI plus BI of x plus CI of x as a polynomial. And we're going to view TJ plus SJ of x plus UJ of x also as a polynomial. And we're going to say that if this polynomial on the left-hand side is included in the polynomials on the right-hand side, then that is going to be a valid lookup. Obviously, we're not working with actual polynomials. We'll need to take a random linear combination in order to be able to make this work. But this is fine because, random oracles absolutely exist, and this is something that we do all the time. So I won't skip that slide. So yeah, you take a random point R, you sort of say, is A1 plus B1 of R plus C1 of R squared included in T1 plus S1 of R plus U1 of R squared, all the way down to T4 plus S4 of R plus U4 of R squared. And then you would just run your lookup argument over this sort of newly constructed table. And the really nice thing about it at all is I was talking about that pre-processing, and you were asking questions about well, what happens if you want to compute your table on the fly? Is this something you were able to do? And I'm there like, well, the pre-processing, it's pre-processing, it doesn't happen on the fly, you compute all of these polynomials in advance. Because they're KZG polynomials, we can add up the random linear combination of the KZG polynomials that we've pre-computed as well. So our pre-computation that we were running for our lookup arguments, we can then take a random linear combination of those, and we've still got our pre-processed values that we actually need. So it all goes through very nicely. So my final thoughts for this lecture and for today is that all of the arguments that I've been giving you are using pairings, with the exception of Halo 2, but Halo 2 is something where we are restricted on the size of our table. What I have not given you is I have not given you any kind of solution that will work in situations where you don't have a pairing-based group. And this is something that does happen. There are people who maybe want to use pairing groups because their architecture or the system that they're using doesn't support it. There are also people that don't like to use them because they've not been standardized. The fact that they've not been standardized, I would say, is quite an embarrassment to our community. They should have been, but they haven't been. Some people don't like that. And one question that we sort of kind of don't know the answer to, like we don't even know if it's possible, to be honest, is can we design a practical and sublinear time lookup argument that doesn't use pairings? Thank you very much.